Hi everyone, I will introduce our paper AutoLoss Zero, searching loss functions from scratch for generic tasks. There are many different tasks in computer vision. To meet the requirement of each specific task, researchers have to design different loss functions by hand and redesign if the performance is not satisfactory. As we can see, the handcrafted design brings high human cost and requires insights and expertise. In this research, we aim to save the trial and error cost for human design by developing a generic automatic search algorithm. Given different tasks and the corresponding evaluation metrics such as the MAP and MLU, we would like to use a unified framework for automatically designing the corresponding loss functions. The framework outputs deployable networks, which is optimized for the given task and the given metric. In this process, there are no additional human costs except for defining the task and the metric. We name the framework AutoLoss Zero as it searches from scratch and with minimal human expertise. However, the heterogeneity of various tasks and evaluation metrics is a huge challenge. To make our framework general to different vision tasks, we should design the search space and algorithm carefully. Specifically, we should use only the basic primitive operators to construct the space so that no task-specific human heuristics are involved. Meanwhile, the search algorithm should be efficient enough to explore the huge space. Here is a list of our candidate operators. The same operator list is used for all the tasks. As you can see, there are some basic mathematical functions and do not involve any designs for specific tasks. The loss functions are represented by computational graphs, with each node selected from the input, output, and the candidate operators. This graph is an illustration of the cross-entropy loss function. The input of the loss functions are the network predictions and the ground truth labels. To explore in this highly flexible space, we employ the evolutionary algorithm for search. First, we initialize the population field with randomly generated loss functions. Then we iteratively improve the population by selecting the well-performed one, mutate it to produce offspring, and update the population by adding in the new loss functions. After several iterations, we output the final population and select the best loss function as a result. Here are the three types of mutation operations. These mutations enable the algorithm to explore the diverse loss functions. However, the naive evolution is too computationally expensive to explore in this huge space. This is because the network training takes a lot of time. To address the issue, they developed two generic techniques for efficiency, named the loss rejection protocol and the graded equivalence check strategy. With these techniques, we can obtain about 5 times of speed up compared with the naive evolutionary algorithm. The loss rejection protocol is used when producing offspring. We develop a fast rejector that efficiently filters out the unpromising loss functions, which cannot optimize towards the target evaluation metric. We repeat the mutation until the offspring passes the loss rejection protocol. As there are a large amount of unpromising loss functions, this technique can skip many unnecessary network trainings. The second technique is a gradient equivalence check strategy. This is to avoid duplicated evaluations of the equivalent loss functions. Specifically, we compute the gradients of each loss function and compare with the previous loss functions. If they are equivalent, we reduce the previous scores and skip the network training. We verify the effectiveness of AutoLoss Zero on a variety of vision tasks. On semantic segmentation, we search for the 6 midstream metrics and achieve comparative results for all the metrics compared with previous loss functions. We also verify our effectiveness on more tasks, such as object detection, instance segmentation, and post-estimation. To verify the generalization ability of the searched loss functions, we conduct experiments on semantic segmentation and object detection on different datasets and different networks. Results show that the searched loss functions can generalize well. At last, we revisit the search efficiency. As shown in the table, with these efficient designs, our search algorithm can explore more than 1 million loss functions in 48 hours. Moreover, the curves of the search process show that our algorithm can largely speed up the search convergence. Thank you for listening. Feel free to search for your own loss function with our released code on GitHub.